Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different.
That was Richard Feynman. He won the Nobel Prize the year after that clip was recorded for understanding the quantum physics of light and how it interacts with matter. But long before he was a famous Nobel Prize winner, as a matter of fact, when he was just a 20-something-year-old grad student, Feynman's first great discovery was an entirely new way of thinking about quantum mechanics, which in the 80 years since has proven essential to our modern understanding of quantum physics. It's called the path integral formulation of quantum mechanics. And once you understand it, Feynman's perspective will give you a ton of insight into the counterintuitive way that things behave in the quantum world. And at the same time, it will teach you how the laws of classical physics, like F equals ma, are derived from the more fundamental quantum mechanical description of nature. Quantum mechanics is all about describing the behavior of really tiny particles, like electrons. And to give you an idea of just how different it is from classical physics, let's start by comparing and contrasting the classical and quantum versions of a very simple problem. So, say we've got a particle that starts out at some position xi at an initial time ti. In classical mechanics, our job would be to figure out where the particle is going to be at any later time. We add up all the forces, set that equal to the mass of the particle times its acceleration, and then solve this equation for the position x as a function of the time t. If it's a free particle, then the solution to this equation is just a straight line. Or if it's a baseball that we're throwing up in the air, the trajectory would be a parabola. Either way, the point is that in classical mechanics, we can predict the final position xf, where we'll find the particle at a later time tf. Quantum mechanics is fundamentally different though. If we're told that a quantum particle was found at position xi at the initial time ti, then all we can predict for when we measure its position again later is the probability that we'll find it here at position xf. If you do the same experiment many times over, sometimes you'll find the particle around there, and sometimes you'll find it somewhere else. This probabilistic nature of quantum mechanics is one of the strangest things about the physics of tiny objects. It means that a quantum particle doesn't follow a single well-defined trajectory anymore in getting from one point to another. In fact, the incredible thing that Feynman discovered, and that you'll understand by the end of this video, is that instead of following a single trajectory like in classical mechanics, a quantum particle considers all the conceivable paths, and it does a kind of sum over all those possibilities. That sum over all trajectories is what's called the Feynman path integral, and it's pretty mind-boggling to say the least. If you're wondering how that could possibly be consistent with the fact that a baseball most definitely follows a single well-defined trajectory, stay tuned. Because understanding how the classical path and F equals ma emerge from the quantum sum over all paths is, in my opinion anyway, one of the deepest lessons in all of physics. I think what I should do right at the beginning here is just give you a quick sketch of how the path integral works and what the main formulas are, just so you have a rough idea of where we're going. Don't worry if it doesn't make perfect sense yet. We'll spend the rest of the video unpacking where it all comes from and what it means. What we're interested in here is the probability for a quantum particle that started at position xi at time ti to be found at position xf at a later time tf. Generally speaking, to find a probability in quantum mechanics, we start by writing down a complex number called an amplitude. And then we take the absolute value of the amplitude and square it to obtain the actual probability. If you saw my last video, you got an idea of how that comes about by looking at a famous quantum experiment called the double slit experiment. I'll put up a link to that if you haven't seen it yet, and I'll also review the key takeaways we'll need from that video in just a minute. So what we're looking for is the amplitude for the particle to travel from point I to point F, and I'll write that as kfi. And here's Feynman's path integral prescription for computing k. Again, classically, the particle would follow a single unique trajectory between these points. But in quantum mechanics, Feynman discovered that we need to consider every possible trajectory that passes between them. Each of those possible paths contributes with a particular weight, which is written as e to the I times s over h bar. H bar is Planck's constant, which is the fundamental physical constant of quantum mechanics. And s is a certain number that's associated to each trajectory, called its action. I'll explain how that's defined later on, but The action is the central object in the more powerful approach to classical mechanics, known as the Lagrangian formulation, which you might have heard about before. I've actually created a whole course all about Lagrangian mechanics. I'll pin a link to that down in the comments, along with a very special offer code for the first 100 students who use it to sign up. And now, to find the total amplitude for the particle to go from point I to point F, we add up these contributions from all the possible paths. This is Feynman's procedure for computing the quantum mechanical amplitude. Of course, the set of all these paths isn't a finite list, so this isn't really a discrete sum. It's a sort of integral called a path integral. And so we more often write it using a notation like this. And that's why this is called the path integral formulation of quantum mechanics. But anyway, now we need to actually understand what the heck all this means. And the intuitive idea behind Feynman's sum over paths starts from the double slit experiment again. So let's begin by quickly reviewing the key things we learned in the last video. Here was the setup. We took a solid wall and punched 2 holes or slits in it. Then we chucked different things at the wall and recorded what made it through to the other side. With classical particles, like BB pellets or billiard balls or whatever, things were very simple. The particles that went through the left hole mostly hit the backstop in the region behind the left hole. And likewise, the ones that went through the right hole wound up on the right. The total distribution was the sum of those 2 curves, because each particle either went through one hole or the other. That gave us one broad bump in the center of the backstop. Next, we looked at waves, like light waves. That was more interesting because the 2 waves coming out of the holes can interfere with each other and produce what's called an interference pattern on the back screen. The bright spots are where the waves add together to make a bigger wave, which is called constructive interference. And the dark spots are where the interference is destructive, and the waves cancel each other out. The corresponding intensity curve looks something like this, with alternating peaks and valleys corresponding to the bright and dark spots. And we discussed how that comes about by writing down the waves coming out of each hole. In complex notation, they were of the form e to the I phi, where the phase phi depends on the distance r from each hole to the spot on the screen. The total outgoing wave is the sum of those contributions, and from that we were able to compute this intensity curve. Finally, we shrunk the experiment down and fired quantum particles at the wall, like electrons. And the result was something surprising. Instead of showing one big bump around the center of the backstop, like we had for classical particles, the quantum particles were distributed according to another interference pattern, with lots of particles clustered in some spots, separated by gaps with next to none. This is nothing like our experience with how things like BB pellets or baseballs would behave. It means that an electron does not follow a single well-defined trajectory on its way across the gap. Each electron somehow probes both holes at once and interferes with itself. Last time, we saw how to describe what's going on mathematically using Schrödinger's idea of the wave function. That's how quantum mechanics was originally constructed, by people like Schrödinger and Born and many others back in the 1920s. In the 40s, though, Feynman came up with his path integral approach. The 2 are completely equivalent. You can derive either formulation from the other. But they each give a valuable perspective on the underlying physics. So now we'll take Feynman's approach and see how the lessons from this simple experiment lead us to the idea of the path integral. The key lesson to take from the double slit experiment is again that a quantum particle doesn't follow a single trajectory like a classical particle would have. We have to consider trajectories that pass through each hole in order to understand the distribution of hits we see on the backstop. But now, let's push that idea a little further. If we drill a 3rd hole in the barrier, we'll have to include trajectories that pass through that hole as well. And the same goes if we drill a 4th hole, or a 5th and 6th, and so on. While we're at it, let's go ahead and add another solid barrier in between, and drill a few holes in that. Now we have to consider all the possible combinations. The particle might pass through the 1st hole of the first barrier, and then the 1st hole of the next barrier, or it could go from the 2nd hole to the 3rd, and all the other possibilities. Now take this idea to the logical extreme. We completely fill the region with parallel barriers, and through each one, we drill many, many little holes. Then we need to account for all the possible routes the particle could take, traveling from any one hole to any other on its way across. In fact, we can imagine drilling so many holes that the barriers themselves effectively disappear. Just like when I mentioned Huygens' principle in the last video. We drill through all the barriers until we're effectively left with empty space again. Then what this thought experiment suggests is that to find the total amplitude for the particle to propagate from this initial point to some final point at the detector, we need to add up the individual amplitudes from each and every possible path that the particle might follow in traveling between those endpoints. And not just the paths traced out in space, but all the possible trajectories as a function of time. And that's how what we learned from the double slit experiment leads us to the idea that we need to sum over all trajectories to compute the total quantum mechanical amplitude. But what weight are we supposed to add up for each path? Let's suppose, much like in our discussion of waves, that each trajectory contributes to the sum with a particular complex phase, e to the I phi, where phi is some number that we assign to each path, which determines how it contributes to the total amplitude. This is the core idea of the quantum sum over paths, and it's pretty incredible compared to our usual experience. We're used to finding a single classical trajectory for the position x as a function of the time t that goes from the starting point to the ending point, where I'll stick to one dimension x here to keep things simple. Maybe it's a straight line or a parabola or whatever. But in quantum mechanics, Feynman discovered that we need to count every possible trajectory that the particle could conceivably follow between those points. For each path, we write down the phase e to the I phi that it contributes, and then we add them all up to find the total amplitude. Strange as it sounds, this prescription is at least totally democratic, in the sense that each term in the sum is a complex number with the same magnitude, 1. You can picture e to the I phi as an arrow in the complex plane. In other words, we draw a picture with the real direction along the horizontal axis and the imaginary direction along the vertical axis. Then e to the I phi is an arrow of length 1 that points at an angle phi. Different trajectories will contribute arrows pointing at different angles, but they all have the same length of 1. The question is, what angle phi are we supposed to assign for each possible path? Well, I already mentioned the answer back at the beginning of the video. For each trajectory, the complex phase it contributes is given by e to the I times s over h bar. H bar is the quantum mechanical constant, called Planck's constant. Its value in SI units is given approximately by 10 to the minus 34 joule seconds. S, meanwhile, is the action, which is a particular number that we can compute for any given trajectory. You might have run into it before because it's something that already plays a central role in classical mechanics. But here's how it's defined. We take the kinetic energy of the particle at each moment, subtract from that the potential energy u, and then we integrate that quantity over the time interval from Ti to Tf. The result is a number that we can compute for any given trajectory, and that's its action. The quantity k minus u that we're integrating here gets its own special name, by the way. It's called the Lagrangian, so that the action is defined by integrating the Lagrangian over time. And that's the central object in what's called the Lagrangian formulation of classical mechanics. And yes, that really is a minus sign in the middle. More on that in a minute. Now, depending on whether you've learned a little bit about Lagrangian mechanics before, seeing the action and Lagrangian appear here might be ringing enormous bells in your head. Or these formulas might look completely out of left field. So let me try to motivate where this weight e to the is over h bar is coming from. Well, first of all, let's just think about the units we have to play with here. We certainly expect Planck's constant h bar to appear in our weight factor, since again, it's the fundamental constant of quantum mechanics. That had units of energy in joules times time in seconds. But phi here is an angle, remember. It's measured in radians, say, and doesn't have any dimensions. So we'll have to pair the h bar up with something else with those same units of energy times time in order to cancel them out. And the simplest thing we could write is a ratio, s over h bar. And the action s indeed has those units we're looking for. K and u are energies, and they get multiplied by time when we integrate over t. Then the units of s cancel out the units of h bar, and we're left with a dimensionless number for the angle phi, like we needed. So the units at least work out correctly. Otherwise, it wouldn't even make sense to write down this quantity, e to the is over h bar. You might be wondering though, why the heck are we taking the difference between the kinetic and potential energy? Wouldn't it seem more natural to write the total energy like we're much more accustomed to? That's certainly what I would have tried first if I'd been working on this problem 100 or so years ago. But that's wrong. It's most definitely a minus sign that appears in this formula for the action. And we'll see why after we've talked about the second key piece of motivation for where this weight e to the is over h bar comes from. It ensures that the unique classical trajectory emerges when we zoom out from studying tiny quantum mechanical particles to bigger everyday objects. It's not at all obvious how that works at first glance at Feynman's formula. If this is telling us to sum over all paths that the particle could follow, each with the same magnitude and just different phases, how could that possibly be consistent with what we observe in our daily lives, where a baseball most definitely follows a single parabolic trajectory? After all, quantum mechanics is the more fundamental theory, and our everyday laws of classical mechanics must emerge from it in the appropriate limit. The answer to this question is one of the deepest insights the path integral reveals about the laws of physics. It will show us how F equals ma follows from this more fundamental quantum mechanical description. Roughly speaking, what happens is that for the motion of a classical object like a baseball, almost all the terms in the sum over paths cancel each other out and add up to nothing. All except one, and that's the classical path. And here's why. Let's draw the complex plane, and here again on the left is a plot of the position x versus the time t. Each term in the sum corresponds to an arrow in the complex plane. It has length 1 and points at an angle set by s over h bar. So we pick any trajectory connecting the initial point to the final point. We compute the action s for that path, divide by h bar, and then we draw the corresponding arrow at that angle. If we pick a different trajectory, we'll get some other value for the action, and that'll give us another arrow at some other angle. And what we need to do is add all these arrows up. Here's the thing though, h bar is really, really, really tiny. Again, in SI units, its value is of order 10 to the minus 34. That's a 1 with 33 zeros to the left of it, and then the decimal point. By comparison, a typical action for a baseball will be something like 1 joule second, maybe give or take a few orders of magnitude in either direction, but it's vastly larger than the value of h bar. And so the angle s divided by h bar will be an enormous number for a typical path for a baseball, on the order of 10 to the 34 radians. Starting from phi equals 0, it's like we flicked this arrow so hard that it spins around and around a bajillion times until it lands in some random direction. But now let's pick a slightly different trajectory and consider what that contributes to the sum. It's a very similar path to the one we started with, so its action will only be slightly different from the first one. Maybe the first path had an action of 1 joule second, and this new one has 1.01, say, so that the change in the value of the action between them is 0.01 joule seconds. It doesn't matter what the precise numbers are, because again, when we divide by the incredibly tiny value of h bar, even that small change in the action at the classical scale will produce a massive change in the angle. In this case, something like 10 to the 32 radians. Then even though these two trajectories were only slightly different, their corresponding arrows point in random different directions in the complex plane. And now, as we include more and more curves, each of them will give us an arrow in some other random direction too. We'll get an incredibly dense array of arrows pointing in all directions around the unit circle. According to Feynman's formula, what we're supposed to do is add up all these arrows for all the different paths, just like you'd add vectors together. But since they're all pointing in random directions, when we add them all up, they simply cancel each other out and seemingly give us nothing. Thus, for a classical object where the actions involved are much bigger than h bar, almost all the terms in the sum over paths add up to 0. Almost. There's one crucial exception. Again, the reason a generic path doesn't wind up contributing anything is that its neighbors, which differ from it only very slightly in shape, have significantly different actions, at least on the scale set by h bar. Then their corresponding arrows point in random different directions, and they tend to cancel out when we sum over many paths. But suppose that there's some special trajectory for which the action is approximately constant for it and for any nearby path. Then the arrows for these trajectories would point in very nearly the same direction, and those wouldn't cancel out. Trajectories that are near this special path would add up coherently and survive, whereas everything else in the sum cancels out. A special path like this, where the action is approximately constant for any nearby trajectory, is called a stationary path. And those are the only contributions that survive in the limit when h bar is very small compared to the action. What that means is, if you start from a stationary path, x of t, and you make a tiny variation of it by adding some little wiggles, say, then the value of the action is the same for the new curve as it was for the old one, at least to first order. That might sound like something fancy, but it's just like finding the stationary points of an ordinary function, like a minimum, say. When you take a tiny step away, the value of the function is constant to first order because the slope vanishes at that point. Finding the stationary trajectory is totally analogous. It's just a little harder since we're looking for a whole path now instead of a single point. But at last, what we've discovered is that in the classical limit, the only trajectory that actually winds up contributing to the sum over paths is the path of stationary action. And yes, the stationary path is the classical trajectory. I've proven that for you in a couple of past videos, and I'll also show you how it works in the notes that I wrote to go along with this lesson. You can get those for free at the link in the description. The notes will go into more detail about a lot of what we've been covering here. But the short of it is, if you plug the definition of the action into this condition, you'll find that a trajectory will be stationary if and only if it satisfies this equation. M times the second derivative of x with respect to t equals minus du by dx. And that's nothing but F equals ma. Because remember, the force on the particle and the potential energy are related by force equals minus the slope of the potential. This is how the path integral predicts F equals ma. It's not that the classical trajectory makes some huge contribution to the sum that dominates over all the other terms. Every term in the sum has the same magnitude, 1. The classical path wins out because that's where the action is stationary. And so the arrows near that trajectory all point at the same angle, and they add together instead of getting canceled out. But that was for a classical object like a baseball. For something like an electron, on the other hand, the size of the action will be much smaller, close to the scale of h bar. So the angles s divided by h bar won't be such huge numbers anymore. And that means that the arrows for non-classical paths don't necessarily cancel out. Then, in the quantum regime, it's not true that only the single classical trajectory survives. There can be a wide range of paths that contribute, and F equals ma therefore isn't very relevant when it comes to understanding the behavior of quantum particles. Oh, and like I promised to explain before, when we defined the action, if we had flipped the sign and used k plus u instead of k minus u, like we might have at first guessed, the equation for the stationary path would have come out the same except with the sign of u flipped. But that would have said that ma equals minus f instead of f equals ma. So we indeed need to take the difference, k minus u, in order to get the correct predictions for classical physics. The fact that the trajectory of a classical particle makes the action stationary is called the principle of stationary action. Actually, more often than not, the classical trajectory comes out to be a minimum of the action. And so it's more common to call this the principle of least action. It's one of the most fundamental principles in classical physics, much more fundamental than F equals ma. And now we've seen how it emerges from quantum mechanics. The principle of least action is the starting point for the Lagrangian formulation of classical mechanics, which I mentioned earlier. And if you want to discover why the Lagrangian method is so much more powerful than what you learned in your first physics classes, you can enroll in my course, Fundamentals of Lagrangian Mechanics. The course will guide you step by step, starting from the basics of F equals ma and working all the way up through Lagrangians and the principle of least action, and all the important lessons this way of thinking about mechanics teaches us. Lagrangian mechanics is an essential subject for anyone who's serious about learning physics, and you'll come away from the course with a much deeper understanding of classical mechanics and the preparation to take on more advanced subjects afterwards, like the path integral approach to quantum mechanics, or field theory, or a dozen other topics in physics that rely on the Lagrangian method. Right now, the first 100 students to enroll in the course using the discount code I pinned in the comments can save $100 off the regular price. So sign up now if you want to take advantage of that and start learning a better way of thinking about classical mechanics. Feynman's path integral is really the quantum version of classical Lagrangian mechanics. It's actually a good story how Feynman came up with all this in the first place, when he was a 20-something-year-old grad student at Princeton. He talks about it in his Nobel Prize speech. First of all, he had a huge hint thanks to an earlier paper by Paul Dirac from 1932, where Dirac realized that the quantum mechanical amplitude somehow corresponds to this quantity, e to the is over h bar. Feynman tells the story of how he was at a bar in Princeton when he ran into a visiting professor who told him about this paper of Dirac's. And the next day, they went to the library together to find the paper, and then Feynman derived the basic idea of the path integral on a blackboard right in front of the astonished visiting professor. I'll link that story down in the description if you want to read it. Now, I've been pretty vague so far about how we're actually supposed to define and compute this sum over the space of all possible paths. And if you're mathematically minded, you've probably been squirming a little in your chair, wondering how the heck to make sense of this formula. Like I mentioned at the beginning, the set of all these paths isn't a discrete list. And so we're not actually talking about a standard sum here. Instead, it's a kind of integral, a path integral. And in the next video, I'm going to show you how we'd actually go about defining and evaluating this thing in a simple example. So make sure you're subscribed if you want to see how to apply the path integral in an actual quantum mechanics problem. In the meantime, remember that you can get the notes at the link in the description, and also check out my course on Lagrangian mechanics. That special offer is only available for the first 100 students who sign up, so don't wait if you want to enroll. As always, I want to thank all my supporters on Patreon for helping to make this video possible. And thank you so much for watching. I'll see you back here soon for another physics lesson.